In some of the earlier models, we had looked at the conventional techniques for evaluating phosphorus in soils. And recently in this module, module 4, we started looking at more of the more recent developments, and of which we talked a little bit on the degree of P saturation and the P saturation ratio. Now, we will try and figure out whether we can merge those two, the old and the new techniques, to understand what happens when phosphorus is added to a soil. So, among the older techniques were isotherm parameters, which could be determined under aerobic and anaerobic conditions. And of course, we will relate that to the P saturation ratio, or the PSR. Just to go back on the isotherm models, see many of these isotherm models, the Langmuir, the Freundlich model, or even the linear KD, these parameters are often used in P-loss predictive models. So it is interesting to know how these can be related to the soil data obtained from the soil tests, such as calculation of the PSR. Now, the Langmuir and Freundlich models we explained in detail in Module 3, Lecture 1, and we know that the advantages of the Langmuir model is that it allows the determination of the soil's maximum capacity to absorb P, that is the P sorption maxima, and also the P bonding energy constant, Kl. We also looked at Kf, which is the Freundlich adsorption coefficient. We did not talk much about the linear KD. The linear KD is measured at low P concentrations, but they also claim that there are problems associated with using the linear isotherm equation in simulating P loss at higher solution P concentrations, such as those that you find when a soil is heavily P impacted. So isotherms can also be determined under aerobic and anaerobic conditions. Now here's just how an isotherm looks. It is simply a relationship of P in solution versus the P retained by the solid phase, that is S prime. And we know from the earlier lectures how we can calculate S naught. So S is the sum of S prime plus S naught. Now, the equilibrium P concentration is the concentration of P in solution where adsorption equals desorption. And here's an example of what EPC actually looks like. We had another example in one of the earlier lectures. Now, the idea behind the whole thing of relating the isotherm parameters to soil test data has been there for a while, though we are beginning to look at it more seriously only recently. We've been looking at it more seriously recently. Here's a relationship of Smax against oxalate extractable iron and aluminum. There is no doubt about it. There is a definite relationship. Then we'll break it out for a while and see how Smax is related under aerobic and anaerobic conditions. So Smax aerobic is on the x-axis and the anaerobic is on the y-axis. And there is a tendency for Smax to be lower under anaerobic conditions. When I say there's a tendency, it falls one way or the other, and the difference does not happen is not that great, especially for a VH horizon of an upland soil. Now, when we turn around and take a look at the SDA, what do we notice? That is the tendency for Smax to be slightly higher under anaerobic conditions, right? This is what we have seen in relations between aerobic and anaerobic conditions and Smax. Now, here we look at a different scenario. Again, aerobic versus anaerobic Smax for uplands, streams, and wetlands. And wetlands showed a slightly lower Smax compared to the uplands. In all three examples, the Smax under aerobic and anaerobic conditions have an approximate 1:1 relationship. So the relationship of Smax under aerobic and anaerobic conditions will vary depending on soil and sediment characteristics. Now, let us take a quick look at EPC under aerobic and anaerobic conditions. The top graph is for the BH, EPC for a BH horizon, and PC for an impacted BH horizon, and you find that EPC is slightly higher under anaerobic conditions compared to the aerobic conditions. When we move along to the SDA, we note that EPC naught is 4 times higher under anaerobic conditions. So EPC under aerobic and anaerobic conditions do not relate to Smax values for the same soils. That is, Smax is not an indicator of P release from a soil. In other words, a soil with a higher Smax could have a lower EPC, whereas a soil with a lower Smax could have a higher EPC value. Now, many of the data here have been taken from older publications, either redrawn or obtained from the basic data existing in some of our older spreadsheets. I'll bring you once again back to the P saturation ratio, or the PSR, because our intent here is to look at the old conventional techniques with the more recent techniques, such as the P saturation ratio, and see whether we can blend or understand the soil phosphorus system better. As we have seen earlier, a plot of PSR against water-soluble P, there is a kink or a change in the slope at about 0.1, and that is what we call as a threshold PSR value. And the threshold PSR, or the PSR itself, is simply a ratio of P divided by iron and aluminum, or factors are in moles, because when you convert or when you divide by the respective, like P divided by 31, it becomes a mole. And the actual P values themselves are expressed in milligrams per kilogram. For more details, please check out the same module, lectures 1 and 2. And note here that the threshold PSR here is actually more for surface samples, and it is about the same for uplands and wetlands, streams, drainage ditches, sediments, and so on. What is different would be for the sporadic horizon, where, if I recall correctly, the threshold value is about 0.05. And the difference in these thresholds is simply because of the form in which the P is held. In the surface horizon, it's the inorganic P relationship, whereas the P relationship with inorganic iron and aluminum P forms, whereas in the BH horizon, it is organically associated iron and aluminum, and mostly aluminum in many of the soils of the Lake Okeechobee Basin. So now here we come to connect the isotherm parameters with the PSR. We have seen a commonly used measure of P retention is the adsorption isotherm. We've seen that in the earlier module, as well as just recently in the same lecture. And this is simply a plot of the amount of P sorbed by the soil versus the amount of P in solution. And the amount of P sorbed is dependent on the iron aluminum in solution. The same is true for the P saturation ratio, which is simply a relationship of P to iron and aluminum in the soil. So there must be some sort of relationship between the old or the conventional techniques and the more recent techniques. Let us look at EPC naught versus PSR. This time we are looking at for the relationship for BH and BT horizons. And what do we notice? When EPC plot is plotted against the PSR, there is a change in the slope, right? The change in the slope is actually, the threshold is a common threshold value of 0.1, but as you know, for the sporadic horizon, the BH, it is much lower, it's 0.05, and then remember, there's also the confidence interval. So this is the general scheme of how the equilibrium P concentration is related to the PSR. And what we do notice is that the equilibrium P concentration is a minimal below the threshold PSR. So if a soil has a threshold PSR below has a value below the threshold PSR, then the EPCs will be essentially zero or very, very low. Now, let us look at Langmuir K versus the PSR. So again, here is a plot of PSR against Langmuir K on the y-axis. And these are for soils from the A, E, and BT horizons. Now what you see here is that after the threshold PSR of 0.1, the Langmuir KL approaches 0, and this is independent of the horizon soil. It doesn't matter which horizon it is basically at 0.1 after the threshold PSR, the Langmuir KL approaches 0. And this is for the A, E, and BT horizons. BH horizons are not included here. So what it does mention, the soil is no longer capable of holding onto P and releases P once it reaches the threshold PSR value. Now we have seen the relationship between Langmuir K and the PSR. Now we went back to really old data that we had and replotted it, or tried to replot it, the K value against the PSR oscillate on the x-axis. Now, and these were done under both aerobic and anaerobic conditions. The P bonding strength decreases, as you can see, under anaerobic conditions. We have seen some of these data earlier, but the Langmuir K follows a similar trend with PSR under aerobic and anaerobic conditions. So there may be some differences below the threshold PSR, but the tendency for the K value as the PSR tends to 0, right? K also tends to 0. That is, there is no further strength of P bonding. It is virtually 0. Now, unfortunately, we do not have many points to show this, but I think the picture is sufficiently clear, and we had, of course, the confirmation from earlier slides. This is data that was derived from some of the really old literature. Now, finally, let us take a look at the Freundlich KF and the linear KD versus PSR. And what do we notice? This is for the A, E, and BT horizons. The picture is pretty much similar to that we have seen for the Langmuir KF against the PSR, right? Again, the story is pretty similar, that once it reaches the PSR of the threshold PSR close to 0.1, the strength or KF decreases, as also KD. They both tend to 0. And here we have a whole lot of references directly related to what we have talked about. These are both references. These are mainly references that relate to the more recent publications, as well, of course, the data that has been obtained from earlier publications and then reassessed.